All right, so in section 2.2, you learned about the simple derivative rules. And what this section is going to do is it's going to take those simple derivative rules and involve them in what happens when we have products and quotients of functions. And we're going to explore that idea in two separate pieces, one for product and one for quotient. So we're going to start with the product rule. So the product rule, the question I am posing is, does this rule work? If I take the product, f times g, and then take the derivative, is that the same as taking the derivative of f times the derivative of g? Because that's what works with addition and subtraction. So it sort of feels like that would be the natural thought that might work here. And so we're going to explore that idea by using a couple of functions and just seeing if it works. So the functions are fairly simple functions because we don't need complicated functions to explore the idea itself. The functions are 4x to the 9th. That's f of x, and then g of x is x cubed. So on the first one, it says we're going to do the left-hand side of the potential equation that we would like to assume. That is that f times g part, and then take the derivative. So if I take f times g, so the f of x is 4x to the 9th. Sorry, that's a little bit big of a pen stroke. Let me move it down one. And g of x is x cubed. And we're going to multiply those first and take the derivative second. So if I multiply these two functions, 4x to the 9th and x cubed together, what do I get?
4x to the 12th.
4x to the 12th, you got it. So this is 4x to the 12th. And then, and then we're going to take the derivative of that. So what's the derivative of 4x to the 12th?
48.
Yes. And that is the derivative of this product. I mean, that's actually, by definition, what it is. The problem is we can't always combine these two functions together in a nice consolidated form like we did on this one. So there's going to be functions later on that you're going to be like, oh, but it didn't look quite like that. And that's because this one was able to collapse together because they were both polynomial pieces, right? So that's not always going to happen. That's why this is a good example to explore whether or not this process works. So what we want to find out is, okay, so if they weren't able to collapse together and I couldn't do the simplification and then take the derivative, is it possible to just take the derivative of each of the pieces of them and then multiply those together? So we're going to try that next. So we're going to take the derivative of f of x, so f prime of x. So what's the derivative of this f of x, 4x to the 9th function?
36 times x to the 8th.
36 times x to the 8th. And what's the derivative of the x cubed function, or g prime of x? X, what was it?
3x squared.
Yep, 3x squared. So our question is if I multiply 36x to the 8th and 3x squared, will I get 48x to the 11th? No, I won't. And you can see it pretty quickly in both pieces, right? 36 times 3 is definitely not going to be 48. X to the 8th and x squared is not x to the 11th. So whatever this is, it's not equal to that one. We don't even really care what it is. It's just not going to be right. What that tells us is that this product rule isn't the product rule. This idea is simply incorrect. And it's usually what we still default to when we sort of forget along the way what to do because it feels so much like the addition and subtraction rules, right? It does. So what is the product rule? Well, the product rule is actually this. We take the original function, f of x, and then we multiply it by the derivative of g. And then we add to that, the derivative of f of x, and multiply that one by g. The order of these things doesn't matter, right? Multiplication is commutative, so I could switch the order of these. So I could put g prime first and put f of x second, right? I also could switch this because addition is commutative, and I could flip these around. And in fact, if you flip those around, that's the definition that a lot of resources will give you instead of the one that I'm giving you. I like to do this in this order. I don't care if you do it in a different order. It doesn't bother me in the slightest. The reason I do this in this order is because I feel like it means you can always start. The first step is just rewriting the first piece. No matter if I get stuck on everything else, I can always start the process because it's a rewrite part. So that's why I do it in this order, okay? But if you have memorized it at some point in a different order, if you're using another resource and you get used to doing it in a different order, that's fine. Do it in whatever order you like. Does everybody have this function or this rule written down? Yeah? Okay, so we're going to use that. So this is an example of one that, much like the sort of like mock example I did over here, we could do without the product rule, okay? So we're going to actually see, in fact, you know what, let me do this before we get to that. Let's go back to the one that we did, and I want to show you it works. I was wanting to show you one worked. It'll be easier to show you this one works than the other one anyway, just a little bit fewer steps. So let's actually use these functions. So we have f of x is 4x to the 9th. And g of x is x cubed. We've already found the derivatives, so let me write them in again too. So f prime of x was 36x to the 8th, and g prime of x was 3x squared. Okay, so this isn't really a proof because you can't use examples in proofs, but at least gives justification that while something failed before and we saw it, it's going to work here for this one. So I'm going to take the f of x function according to what this says. Well, f of x, we know what the answer is supposed to be. It was supposed to be, what do we have? 48x to the 11th. This is what it should work out to being because that is the correct answer when we collapsed them first and then took the derivative second. All right, so if I take f of x, which is 4x to the 9th, and I multiply it by g prime. So g prime's down here at the bottom, that's the 3x squared. And then I take the derivative of f of x. That one was the 36x to the 8th. And I multiply it by g of x, which is x cubed. And we're going to do a little bit of algebra to simplify. So in the first one, I have 4 times 3, which is 12. X to the 9th and x squared is x to the 11th. That's good because we're supposed to be getting some x to the 11th, right? And then I've got 36 times 1, or 36. X to the 8th and x cubed is x to the 11th again. And what is 12x to the 11th plus 36x to the 11th?
48x to the 11th.
It is 48x to the 11th. So this example really didn't need the product rule. It didn't. We could actually multiply and simplify things beforehand and then take the derivative. But if we've used the product rule, we will get the same thing. The same is true for, whoops, this one right here. For this one, because these are just pieces that are polynomials, we could FOIL this out if you wanted and then take the derivative, right? We could totally do that. There'd be no problem in doing that. But we want to practice using the product rule on something that's easy to use the product rule, right? The pieces are easy, and then we'll get them more complicated as we go. So with the product rule, here's the way that we think about it. So we're going to take the derivative. The first piece, in parentheses, I'm just going to drop it down and rewrite it. So this is x squared plus 3. Rewrite the first piece. And then I need the derivative of the second piece. So what's the derivative of x squared minus 5? Yeah, 2x. Product rule uses addition, so I'll add between these pieces, and then I do the opposite. So originally I just rewrote the first piece. Now I need to take the derivative of the first piece. So what's the derivative of x squared plus 3? 2x, again, but for a different reason, right? Different function. And then I rewrite the second piece, x squared minus 5. Now, I'd like to pause here and make a comment. When you get to the gateway, which is the end of next week, next Friday we're going to do a gateway exam. Your gateway exam is going to look like this. You're going to have a function like this. You're going to have functions like you saw back in section 2.2, and you're just taking a derivative and you're not simplifying anything, and you would stop right here. If you simplify and you make a mistake, we'll count it wrong. So don't simplify. Just stop right here, and you're good to go. For the purposes of homework and for the purposes of tests and things like that, quizzes, we should simplify what we can. So we will. It's often been said that students don't get good at algebra till they take calculus. You're going to do a bit of algebra here, right? We're going to simplify some algebra going on. So that's what our next step is. So our next piece is going to be to multiply through here. So I have x squared times 2x, or 2x cubed. And then 3 times 2x, or 6x. All right, what about the next one? When I distribute the next one through, what do I get?
2x cubed minus 10x.
Very good. 2x cubed minus 10x. Okay, is that good for everyone? Combining like pieces, how many x cubes do I have? 4. So I have 4x cubed. And then how many x's?
-4.
Negative 4x. And we would actually be done at this point. And I'll put g prime of x over here just so I can put it all inside the box. So that'd be our final answer as far as being cleaned up and in the right form, a reduced, simplified form. Okay, any questions on that?
I looked down for a second. I missed how we got the x squared minus 5 times the 2x off of the, like, where'd the 2x come from?
Do you mean this 2x right here?
Yeah.
It came from the derivative of this piece. So the derivative of x squared plus 3 would also happen to be a 2x. I should probably change this example since they both can be 2x's. It looks a little bit funny.
I see.
But
So
yeah,
the derivative.
the derivative of the first
Okay,
piece.
okay.
Right.
Cool.
Yep. Any other
They just
questions?
happen to be the same.
It just happened to be the same, right? Even as I did it, I thought, you know what, I don't think I've ever noticed when I've done this before that could look confusing. They do happen to be the same.
Okay.
Okay? Let's try another one. So on this one, we don't have a choice. There's no way to actually combine x cubed and cosine x. It's not possible. Right? It was possible in the first 2 examples that I did. I could combine them if I wanted to, and I could take the derivative second. I can't even do that here. It doesn't make any sense. So the product rule is absolutely critical at this point because it's the only option we have. So we're going to do the derivative. Whoops. Let's try that again. Derivative of f. First piece just gets rewritten. That's the easy part. We can always start x cubed. What then is the derivative of cosine of x?
Negative sign.
Very good. Negative sine of x. I have addition. What's next?
3x squared.
Yeah, derivative of x cubed, so it's 3x squared. And finally, I just simply rewrite the second piece, cosine of x. And the very nice thing about this one is, aside from the negative that's beside the sign that I'm going to move to the beginning, there's no simplification that we do. There simply just isn't anything here to condense or to reduce. So I'm going to pull the negative to the beginning, but that's the extent of my ability to do anything else. And we're done. And again, on the gateway, you don't even have to pull that negative to the front. I mean, if you did, I don't think you'd probably make a mistake in doing it, but there's no need. You can just simply stop at the first step. All good? All right. So what about the quotient rule then? You probably are thinking, I bet it doesn't work, right? Product rule didn't work, quotient rule probably won't either. So we would think, again, by our sum and difference rule that we had, that we might just be able to take the derivative of the numerator, the derivative of the denominator, and stick them in. And again, that's the default that people get to when they blank when they see this sometimes too, because that seems like it fits with some of the other things we've done. And so we're going to use that same 4x to the 9th and x cubed that we did before, and we're going to do the same thing we did before, and we're going to try and see if it works. So these two I like because you can condense them, and you can actually see whether or not the process works at a like a just quick glance. So we're going to first divide 4x to the 9th by x cubed. What is 4x to the 9th divided by x cubed?
4x to the 6th.
4x to the 6th. And what is the derivative of 4x to the 6th?
24x to the 5th.
24x to the 5th. Very good. Okay, is that all right so far? Okay, so that's the answer. It's the answer because I did the algebra first. I can't always do algebra first, but that is the correct answer. What we want to see is if we have the ability to do the derivative, that's the word I want, the derivative on the top and the bottom separately, and it still works. So the derivative for the top, we've done this before. It was 36x to the 8th, right? That's the derivative of 4x to the 9th. And the derivative of g prime of x was 3x squared. And then we're going to divide. So what's 36 divided by 3? 12. And all of a sudden, it doesn't work, right? And just to further confirm it, the x to the 8th and then the x to the 2nd is x to the 6th, right? So this does not equal this one. They're not the same. This is not the quotient rule. It doesn't work. So what is the quotient rule? Well, it's messy. That's annoying, I know. Now, write it down, and then I'll give you some mnemonic devices that might be helpful in remembering them. You might look at that numerator and say, well, that kind of feels like the product rule. And it kind of does, right? The only difference is there's a subtraction sign in between. And the other thing that you might notice is that it's flipped. Right? It's flipped from the way I wrote my product rule. So I don't start with the top part. I start with the bottom part. The denominator is just simply the denominator squared, so that's not a complicated piece of it. You can't reduce this. This is the reduced, you can sometimes reduce the algebraic components when you do problems, but you can't reduce this expression. This is the only way this expression can be written in a reduced form. So I will show you a couple of different mnemonic devices. I'll show you the one that I learned when I was first learning calculus, and then I'll show you one that a subsequent teacher of my daughter had used that I thought was pretty cute too. So the one that I had learned was to call this one high and this one ho. Okay, that's what I learned. And the teacher did something like this. Hody high minus Heidi ho all over ho ho. That's how I remember it. So even to this day, when I do quotient rules, this is what has been going on in my brain because that's what I learned. Does anyone know where Heidi ho comes from? You guys don't get to tell. I don't know if you remember or not. A couple of them have heard me tell this before. Does anybody know where it comes from? It's a sitcom. It's an old sitcom. My kids have watched it, but they've watched it because we bought the series. It's from Tool Time. Tim the Toolman Taylor, Tim Allen. And, It's from that. Yeah, Heidi ho. Heidi ho. It's the neighbor that says it to him across the fence that you never see his face, Wilson. Yeah. Yeah, so that's where it comes from. So I think that's probably partly why I remembered it, is because that was part of, something my family watched together. So this is one option. So obviously you can just remember it the way that it is too, and all the pieces. But this is one option. This is the other one, and I'm going to hope that I don't mess it up. And if I do, don't tell Dr. Drake on me, because this is from him. So his is high and low, which I like that. That's cool, right? High and low. You can certainly see why that would make sense. And it looks much the same as my top. So it says Lodi high minus Heidi low. All over low, low, and away we go. That's what he says, and away we go. So my daughter kind of liked that one when she took Calc 2 with Dr. Drake. She thought that was pretty clever. She didn't like mine as well, I don't think. That's okay. I don't care how you remember it. The most common mistake that I see students doing, if they're not doing just take the derivative of the top, take the derivative of the bottom, right, is to switch the numerator around and have the numerator flipped backwards. So that's a word of caution to you. Make sure you're getting the numerator in the right order. It always starts with the denominator piece first. Before you do any derivatives, the denominator piece starts first. So we're going to do one. You ready? We're going to do the one that we actually just did, because we should see that it actually works much like we did before. So we had f of x. Actually, you guys can write it. I'm going to just copy it from my previous slide. These were our pieces. It's kind of cheating. I'm sorry. Okay. So our f of x is 4x to the 9th. Our g of x is x cubed. F prime and g prime were the ones we've seen before, of course, too. And so we start with the denominator, low or the ho part. So the low part, or the part on the bottom, is x cubed. And I take that times the derivative of the numerator, f prime, or the d high. So d high is 3x to the 6th. Sorry, not 3, 36. 36x to the 8th. Too much zooming in and zooming out, so sorry. 36x to the 8th. Minus. And then I need the high, like just the high itself, the part that it started out as. That was 4x to the 9th. And that's multiplied by the derivative of the denominator, d ho, or d low. So the derivative of the denominator was 3x squared. All that's divided by the denominator squared. Low, low, and away we go. X cubed squared. Or you can write x cubed if you prefer. So on a gateway, you stop there, right? You do. For all the other work that we're going to do, we're going to simplify what we can. Sometimes we can simplify more than others, just like with the others we've seen. So this first piece, we've seen this before. This is 36x to the 11th. But now it's minus. And this one was 12x to the 11th. What am I going to be dividing by? What is x cubed squared? X to the 6th. Good job. The numerator, 36 minus 12 would be 24. So 24x to the 11th divided by x to the 6th. And what does that give you? You subtract, What we got? 24x to the 5th. Is that what we got on the previous page? 24x to the 5th. It is, right? Worked out. So that's at least validity. It makes you feel like that the pieces work and it was valid. The other piece for certainly did not. Okay, you ready to try a different one now? Okay. Sometimes you can simplify a fair bit, even when they're not this simple. Sometimes you can't. Sometimes there's really just very little you can do. So this is going to be an example of one where there's not going to be a whole lot we're going to be able to do when we get to the end of simplifying. But it is a good example of one that needs the quotient rule. There's no way to condense that numerator and that denominator because I've got the addition and subtraction of the pieces involved. So I can't reduce this and actually do it any other way. So we're going to take the derivative. And I start with what? Where do I start?
With the denominator.
With the denominator, okay? Low, the low part. So 5t minus 3. Start with the denominator. And then I take the derivative of the numerator. So what's the derivative of my numerator?
2t.
2t, yep. Product rules are addition, quotient rules are subtraction. So this one's subtraction, because I'm doing a quotient rule. And I need to flip the pieces that I just did. Previously, I did the denominator as it was. Now I need the derivative of the denominator. So what's the derivative of the denominator? Or, hang on. We'll do the numerator first. If I'm following my pieces, I'll do it. So high, I'll do the high part first. So that one would be 2t squared plus 4. Then I have my derivative of my denominator. So what's the derivative of my denominator? 5. And all of this is over
5t minus 3 squared.
5t minus 3 squared. And I'll tell you right now that there's seldom a need to square that and actually distribute that out. That is not an expectation. That does not simplify anything. At worst, it makes it harder to see places where you can simplify. And at best, it just makes it bigger and uglier. That's not necessary. So you can always leave that denominator in factored form. There's no reason to ever multiply that out. Okay? In the numerator, however, we will simplify and multiply the pieces out. So I have the 2t multiplying through. So what does that give me?
10t squared minus 6t.
Very good. 10t squared minus 6t. On this other one, I have the 5 and I have the negative going through. So if you want to think about multiplying, I'm really multiplying a negative 5 through all the pieces, right? Because the negative is affecting things as well. So if I distribute a negative 5 through the t squared plus 4, what will I get?
Negative 5t squared minus 4.
Yep. And it's over that same denominator squared. All right, simplification in the numerator, what do you see?
5t squared, which is going to cancel.
Yep, these two pieces. It's not, well, okay, these two condense. And then what else do I see? Anything else reducing? No, I just have to write them right. I have negative 6t and have minus 20. The denominator is 5t minus 3. In order to reduce anything with the denominator, you have to have a factor, not a term, but a factor of 5t minus 3. Now, there is a 5t in my numerator, so it sort of seems reasonable that I stand a chance of that happening. If I factored the numerator, I'd have one piece that would say 5t. The problem is that the 20 at the end has no way to be factored to give me an ending value of 3, right? 20 doesn't divide by 3. So there's no way to get a factor that has a minus 3 at the end. So because that's the case, I don't really care if the numerator factors. There's no need to try and factor it because it simply won't factor in a way that reduces. And if it won't factor in a way that reduces, then we're done. Okay? So you have to think through that. You have to check it because if it does factor in a way that reduces, you need to. But if it doesn't, don't do more work than is necessary. So we're finished. This is g prime of t. Okay, I think we're going to do one more today, and then we will pick up on the derivatives of trig functions next time. This lesson is supposed to span Friday to Monday, so that was the plan anyway. So one more question, I think, ends us at a really nice section. So we'll do one more question, one more quotient rule problem, and it's trig, kind of like we already did one trig, one with the product rule, right? So with trig and polynomials involved both, like with the quotient or with the product rule that we did before. When this happens with the quotient rule, there's no way to simplify this. The quotient rule is the only option that we have. So we're going to do h prime of x. And how will we begin?
With the denominator.
With the denominator. The denominator is x cubed. Good place to start. Then what?
The derivative of the numerator.
Yeah, so what's the derivative of sine of x? Cosine of x. Very good. What's next?
The numerators. Or the negative sign.
The negative sign. First we're going to subtract, and then we want the numerator. Yeah. So that's sine of x. And
3x squared.
3x squared. Okay, everybody good with the numerator of the quotient rule? That part okay? Okay, what's in the denominator?
X cubed squared.
X cubed squared. You kept trying to decide if you just wanted to say x to the 6th, didn't you? Yeah, it's okay. And if you jumped to the point and you said x to the 6th, it would be totally fine. Yeah, we do have x to the 6th as our denominator. Notice, though, I'm going to rewrite just a tiny bit. So again, on the gateway, you would stop before I did the x to the 6th, or if you did x to the 6th, it'd be fine. But you wouldn't have to go any further. But this one will reduce. So take a look. We have x cubed cosine of x minus 3x squared sine of x. Correct? Every term has an x in it. There's an x cubed, 3x squared, and x to the 6th. Right? So there's a couple of things that you could do. Well, there's one thing you can do. There's a couple of ways to show it. If you're okay with seeing it at this point and simply reducing it from all pieces, that's all right. Or you can factor it out to reduce it. So I'm going to show you the factoring it out to reduce it. If you just reduced it straight from here, it would end up collapsing pieces where the x cubed and the x to the 6th can only be divided by x squared because they have to have both of them in it, right? So this would be an x sine x minus 3. I don't mean sine x, I meant cosine x. Sorry about that. X cosine x minus 3 sine x. And it would be over x to the 4th. So if you just reduce it from there and that makes sense to you, what I just did, then you're good to go. You can do that. If you're like, where did all those pieces go? Another way to see it is to simply notice that they have an x squared in common. So I can factor x squared out, and then I have x cosine of x minus the 3 sine of x over the x to the 6th. And then this squared and this 6th will reduce, right? Subtraction of exponents kind of stuff from college algebra. And we would end up getting the same thing, x cosine of x minus 3 sine of x over x to the 4th. So whether you need to see the factoring out or whether you're good without it, don't care in the slightest, but either of those options would work. You'll end up with the same answer. Okay, any questions on that? Okay, so we will pick up with the rest of this lesson on Monday.